dear students who joined over here. Once again, a warm welcome for this second lecture of the lecture series on signal and image processing. So, as I told you, today we can have the possibility of discussion we may have at any point of time. If you face any difficulty in understanding, you can raise your hands and you can even turn on your mic and ask the questions. Okay, so initially what I'll try to do is I'll try to have a simple recap of the things what we have learned in the last class. So in the last class, actually, we try to define two vectors. We define the vectors and we consider two vectors g bar and x bar, and we try to calculate the component of g bar along x bar. We try to calculate this along x bar, and we found that the component c is equals to g bar dot x bar under divided by mod x bar square. So this is the component what we have uh, derived in the last class. And the thing is, a similar thing we also derived for the signals. We have taken the analogy of the vectors towards the signals, and we found that we defined two signals we defined, and the two signals g of t and x of t we defined, and we would like to find out the component of g of t in the direction of all, I can say, g of t, component of g of t along x of t, and we define it as the c is equals to 1 divided by ex eg integral t1 to t2 x of t g of t dt. In x of t g of t dt, that's what we have defined. And if I'm not wrong, I should make this as ex only, because the similarity of this x bar square will be having ex. Okay, so this is what we defined. If you are more specific, that means if you would like to fix more specific about the interval, then I can able to write this as c is equals to divided by integral t1 to t2 x square of t dt. Actually, this is what we have defined in the last class. Later on, what we have seen is the orthogonality. We talked about something like orthogonality. So orthogonality we try to define. Usually the term orthogonality we will be using for the signals, orthogonal signals. Otherwise, for vectors it is perpendicular. So for the vectors, two vectors are said to be orthogonal or perpendicular if and only if g bar dot x bar is equals to 0, where g bar dot x bar is equals to, we also given the definition for the dot product, mod g bar mod x bar cos theta. So when theta is equals to 90 degrees, then you will be having this orthogonality condition. And for the signals case, we defined two signals are said to be orthogonal if and only if integral t1 to t2 x of t g of t dt is equals to 0. Okay, so if you try to satisfy this condition, then you can say that these two signals are orthogonal in nature. We also have taken the example of two signals, that is a sine theta and sine 2 theta, sine theta and sine 2 theta, and we observed that these two are orthogonal in nature. For that matter, we also took the sine theta and cos theta also, sine theta cos theta also we have considered as an example, and then we verified that even sine theta and cos theta were also orthogonal to each other. Now we also defined this orthogonality condition for complex signals. So for complex signals, the condition for orthogonality is integral t1 to t2. If you want, you can put x of t into g star of t dt, which is also equals to integral t1 to t2 x star of t g of t dt is equals to 0. So we defined actually the real signals and complex signals. We defined real and complex signals. We even defined the energy signals and power signals. So this is a complex signals, and the above one what we have defined over here is this is for real signals. Real signals. This is the condition for real signals, and this is the condition for the complex signals. So this is what we have seen in the last class. Okay, and the most important thing is the energy, the term energy of the signal. You try to see here. I can use let me use the denominator over here in the component. Of course, this also can be defined. This will be mod. Actually, this will be mod x square of t for complex signals. Mod x square of t. Mod. Oh, yeah, I should write this mod as mod over here. So for complex signals, the equation how will it will gets modified is you will be having x square of t. So you will not have this. So that is for the complex signals, because we will be taking the magnitude. And if you try to compare this denominator and this denominator, you can able to say that there is some analogy between the magnitude of a vector and the energy of a signal. So yes, there is an analogy. There is an analogy between the magnitude of a vector and the magnitude of a vector and the energy of a signal. Okay, so we even defined the energy signal and power signal. So energy signal and power signal. So energy signal and power signal, we define that if the energy is finite, obviously power will be 0. So those are called energy signals. And if energy is infinite and power is finite, which is non-zero value, then it is called a power signal. So this is the way how we define the energy signals. And more or less all periodic signals are energy signals. Usually all periodic signals are energy signals. And periodic signals usually comes into the category of energy signals because they were defined for a period, for a fixed amount of period. If you try to remember in the power, when you try to calculate the power equation, there 1 by t times integral minus m2 plus m2, you'll be doing that 1 by t tends to infinity there. So that means the signal is extended from minus m2 plus infinity. So in that case, you'll be having a finite amount of power, and energy usually will be infinite. Okay, so this is the two types of signals that we have considered: real and complex signals, energy and power signal. Now today what we are going to do is, today the agenda of my lecture is comparison of the signals. We'll try to see comparison of the signals, and before going to that, I'll be giving you a small 10 minutes duration explanation on the energy of the sum of the orthogonal signals, because we defined the condition for orthogonality. So how it will be if I would like to calculate the energy of two orthogonal signals. In other words, how it will be if I would like to calculate the magnitude of the sum of two orthogonal vectors. Magnitude of the sum of the two orthogonal vectors. This is very simple. It's not a big issue. You people might know this thing very well. but I'll try to make it in a mathematical form in a very systematic way. Okay, so let me start the topic of energy of sum of orthogonal signals. So I'll try to start with again vectors. I'll try to take again two vectors. That is, let me assume this is some x bar and this is y bar, which are orthogonal to each other. And let me assume this is z bar. And as per the law of triangle of vectors, you can able to write this as z bar is equals to x bar plus y bar. And if I try to calculate the magnitude of z bar is equals to magnitude of x bar plus y bar. Magnitude of x bar plus y bar. Okay, and we know that Pythagoras theorem, if I try to follow as per Pythagoras theorem, we will be having mod z bar square is equals to mod x bar square plus mod y bar square. This is what the Pythagoras states. Now, if this is the case with the orthogonal vectors, can I apply the same thing for signals? Yeah, let's try to do that thing now. So if I try to have two signals, one is x of t and y of t, and what I would like to say is I would just want to verify whether z square of t, or in other words, I can able to say that energy of the signal z of t. Energy of the signal z of t. So energy of the signal z of t means E z. Let me assume Ez square is equals to Ex square plus Ey square. This we are going to do because my z of t I am going to represent in terms of two orthogonal signals, that is x of t plus y of t. So if this exists, then can I write like this? This is what we are going to verify now. So to verify this, what we will try to do is we will try to calculate the energy of the signal z of t. We will try to calculate the energy of the signal z of t. So energy of the signal z of t, Ez is equals to integral. Okay, if you are more specific about the time, t1 to t2 z square of t dt. Z square of t dt. This is what we are going to have. Okay, so now let us try to do the squaring on both sides, but that squaring we will try to do little later. What I would like to do over here is, which is equals to integral t1 to t2. Z of t means you will be having x of t plus y of t whole square dt. Z of t is equals to, so actually the thing is, it is the sum of the energies. It is not the square of the energies, it is the sum of the energies. Ez is equals to the energy of Ex plus energy of Ey. Okay, so you will be, if you try to expand this equation, you will be having integral t1 to t2 x square of t plus y square of t plus, if it is complex, if the signals are complex, x of t and y of t are complex, then I supposed to write x star of t multiplied with y of t plus x of t multiplied with y star of t. This is what I supposed to write if the signals are complex in nature. Otherwise, I can straight away write 2 into x of t, y of t I can write. And remember one thing, because x of t and y of t are orthogonal in nature, I can able to write this as integral t1 to t2 x square of t plus integral t1 to t2 y square of t dt. The remaining terms does not exist because when you try to integrate two orthogonal signals within the period of t1 to t2, then this will goes to 0, and even this also goes to 0. These two will goes to 0. Okay, so that's what is being happened when you try to perform the integration, and hence if you try to check it out, these two, you'll be getting ex plus ey, which is exactly the same as that of your Pythagoras theorem for your vectors. That means the energy of the signal z, which is equals to energy of x plus energy of y. Okay, those people who are familiar with Fourier series, this is for the people who are familiar with the Fourier series. We are going to represent the signal x of t in terms of cos and sine terms, function of cos theta and sine theta. So you'll be having an infinite number of cosine terms, infinite number of sine terms, and if you try to see over there, each and every function cos theta, or I can able to write it as cos n theta, because n is going to vary from 0 to infinity. N is going to vary from 0 to cos 0 theta, cos 1 theta. So cos 0 theta is 1 and cos theta. These two are orthogonal in nature. 1 and cos 2 theta orthogonal. 1 and cos 3 theta. They were orthogonal to each other. Likewise, 1 and sin theta is also orthogonal. 1 and sin 2 theta were orthogonal. That means if you like to calculate the energy of the signal x of t, it will be very good if you try to calculate the energy of each and every component, each and every orthogonal component that will help you to represent the signal x of t. Because see, the Fourier series representation is same as representing a vector in free space in its unit vectors, that is x direction, y direction, and z direction. There is nothing new over here. You can able to have a very good analogy of representing a vector. For suppose the second years might be having the cylindrical coordinates and spherical coordinates. What we are going to do over there we are going to represent a vector in the free space in terms of the rho theta and phi. Rho theta and or r theta and phi in spherical coordinates, rho phi and z in the case of cylindrical coordinates, rho phi and z in the case of cylindrical coordinates. So the thing is, representing a signal in terms of Fourier series, is the same as representing a vector in a free space. Particularly, you can have as I told you, the complete set should be there. Yesterday we even defined the complete set. What does the complete set means? You should not find another vector that is perpendicular to all these three vectors, all the vectors that was already available. For suppose if I try to consider xyz coordinate system, then you will not find any vector that is perpendicular to x, y, and z. Even the same is the case in cylindrical coordinates, rho, phi, and z. Even with spherical coordinates, that means those three unit vectors, rho, phi, z, r, theta, phi, these three will be forming the complete set. Likewise, here, when you try to represent the signal x of t in terms of cos and sine terms, whatever the signals that you are going to have, if you want me to write, I can able to write here. Anyway, we will be seeing this Fourier series sometimes later. So for cos, you'll be having 0. Cos 0 is 1 actually. So 1 comma cos theta, comma cos 2 theta, comma, and so on. That's it. Infinite duration. Then 0 sine theta, sine 2 theta, and so on. So these signals will be forming a complete set. That means you will never find any signal that is perpendicular to the signals that was available over here. That's what I want to say over here. And yeah, of course, the Fourier series is the very basics for the other transforms that we are going to define. See, as I told you, in the spatial coordinates, particularly XYZ rectangular coordinates, XYZ are called rectangular coordinates. Were there any other type of coordinates where we can able to represent the spatial vector? Yes, cylindrical coordinates, spherical coordinates. Now, in the case of signals, we are going to have in so many of such type of coordinate systems. So in spatial coordinates, usually we try to consider rectangular, cylindrical, spherical. These are the three different types of coordinate systems that you can able to have to represent any vector in the free space. So likewise, to represent any signal you are going to have I cannot say infinite, so many representations you can able to have. Okay, so those representations were actually considered as the different types of transforms. Whatever the transform that you are going to define, that will comes under the representation of a signal in terms of another variable. Okay, representation of a signal. Now, so this is what I would like to say as of now. So we try to verify the Pythagoras theorem, particularly in the case of signals. So Pythagoras theorem in the case of signals means Pythagoras theorem says that the magnitude of a vector hypotenuse is the square of hypotenuse is equal to sum of the squares of individual vectors, particularly for a right angle triangle. Okay, so which is equivalent to, that means what I can say is this uh, mod z bar square plus is equals to mod x bar square plus mod y bar square. These two are equivalent. This is for vectors and this is for signals. Okay, so now let me move on to the actual topic of today's lecture, that is signal comparison. So comparison of signals is very much required. Comparison of signals is very much required. Because we are dealing with signals, I gave the title signal comparison, but while we start discussing, I'll be starting with again the vectors. So again, we'll try to consider the two vectors g bar and x bar, let us assume. And these two vectors, you can able to say that they actually, we define one thing, that is orthogonality. These two are orthogonal. These two are orthogonal if and only if g bar dot x bar is equals to 0. So this is what the orthogonality condition is. Fine. Now similarity means see, we are going to represent g bar is nearly equals to c into x bar, and we define the value of c, that is the component along, what is the component of g bar along x bar that we try to define, and the component c is given as c is equals to z bar dot x bar divided by mod x bar square. Mod x bar square. Whenever you try to calculate the similarity of these two vectors, it should be very, that means similarity means it again depending upon the value of c. Am I right? If c is equals to 0, they were orthogonal in nature. So if c is large, c is large means there is a large component of g bar along x bar, then I can able to say that the vector g bar is similar to x bar if c is very large, and if c is very small, then I can say that there is no similarity between the vectors g bar and x bar. And when you try to calculate this thing, the most important thing that will comes across is the magnitude of a vector. So the why I'm saying the magnitude of a vector is, for suppose, because we are going to talk the similarity based on the value of c, and the value of c is going to depend upon the magnitude. The value of c is going to depend upon the magnitude. So if I try to increase if I try to multiply the vector g bar with some constant k, if I multiply the vector g bar with some constant k, then you'll be having the value of c even much more greater compared to that of previous one. So k times the previous value. So does that mean that it is going to have more similarity? Is that a good similarity measure to find out? So, okay. The second thing, if I try to multiply the vector x bar by 2, let us assume. So what happens? The numerator will be 2 and the denominator will be having 4. So C will be reduced by half. So the similarity index C, which is going to indicate by C, is a function of magnitude, and that's not what we would like to have, because even if you try to multiply it with some constant, that similarity index should not get affected. So because of that reason, we will be defining the normalized coefficient, normalized value of C. Normalized value of C, we will be defining it as Cn, which is called the normalized C value, and we try to define this as cos theta, just cos theta. Actually, the reason is theta is going to give whether those are similar or not. So it doesn't depend upon the magnitude. It depends upon the angle between the two vectors, g bar and x bar. If this is x bar and this is g bar, so it depends upon the angle, whether the magnitude of the vector is 100 or 1000, it doesn't matter. Your similarity index should not include the magnitude. Okay, if it includes, means it's not the appropriate measure to find out the similarity between two vectors. Okay, because every time when you try to increase the magnitude, then the similarity index of C also will get affected, right? So that is the reason why we are going to consider Cn, the normalized coefficient of C, that as the similarity index, and this is given by g bar dot x bar divided by mod g bar and mod x bar. This is the way how we are going to define the similarity index, and we call this as correlation coefficient. We call this as correlation coefficient. Cn is called correlation coefficient. C bar is called correlation coefficient. Okay, now if I try to observe the what values it is going to take, and the very first thing what you would like to observe is whether it is going to have the effect of magnitude or not. Okay, fine. If I try to multiply the vector g bar with some 10, both numerator and denominator also will get multiplied with 10, and hence you don't find any effect on the correlation coefficient. So normalized correlation coefficient, actually this is. So from this you can able to say that, from this particular equation, correlation coefficient, you can able to say that the Cn is going to have the values between -1 and +1. Cn is going to have values between -1 and +1, and is independent of the magnitude of the vectors. So now we are going to use this to identify whether these two vectors are similar or not. Okay, now what will happen when Cn is equals to +1? Cn is equals to +1 means Cn is equals to +1. Cn is equals to +1 means you can able to say that those two vectors are aligned in the same direction. So that means there is a maximum similarity that you can able to have between those two vectors. So that means that theta will be equals to 0, and hence you will be having cos theta value 0, cos 0 value is 1. So maximum similarity we are going to have when Cn is equals to +1. That means these two signals are, these two vectors are similar. Yeah, the same concept will be applying for the signals as well. Keep hold for a while, because we'll be moving to signals also very shortly. Now when Cn is equals to -1, we can say that a maximum dissimilarity we will be seeing maximum dissimilarity between these two vectors. And when Cn is equals to 0, when Cn is equals to 0, you will be having these two vectors completely orthogonal. Yeah, is there any difference between maximum dissimilar and orthogonal? Yes, there is a difference. Yes, there is a difference. What is the difference? So it is something like, if you try to consider, I'll be using 3 phrases over here. Three phrases I will be using. One is, yeah, that I'll be explaining it to you when we move on to the signals. Let me go ahead, because the maximum similarity indicates that these two are in the same direction. Both x vector x bar and g bar both are in the same direction. This similarity means one vector in this direction, another completely opposite to each other. And orthogonality means you will be having the perpendicular region. The angle will be 90 degrees. The angle will be 90 degrees. Now, if I try to apply the same concept, and if I would like to define the similar correlation coefficient for signals, how it will be? See, the dot product in the numerator g bar dot x bar, we will be defining it as the integration of the product of the two signals g and x, and usually we will be considering this integration from minus infinity to plus infinity, and the denominator mod g bar and mod x bar will be writing it as the energies of the signal g bar and x bar under root. So that means the correlation coefficient for signals, your Cn will be equals to 1 upon under root Ex multiplied with Eg, energy of the signal Ex and energy of the signal G, which is multiplied with integral minus, usually we will be considering this from minus infinity to plus infinity interval, G of t multiplied with x of t dt. This is what we will be defining as a correlation coefficient between two signals. This is the correlation coefficient between two signals. So this will help us to identify whether the two signals are similar or not. Multiplying either side, multiplying either g of t or x of t. You try to remember one thing. I am just increasing the amplitude of g of t and x of t. If I try to multiply either g of t or x of t by any constant, it has no effect on my correlation coefficient. That's one of the important things that you are supposed to know. Now, if this is the case, let us try to find out the range of this correlation coefficient for signals. So, as per the Schwarz inequality, we have the equation integral minus infinity to infinity g of t multiplied with x of t dt whole square is always less than or equals to integral g square of t dt multiplied with integral x square of t dt. Yeah, you might be wondering what is this, right? So I'll tell you one thing. I'll try to tell you one thing. So let us consider an integration. Consider an integration integral lambda into x of t minus g of t. Yeah, let me stop it over here. The thing is, if you try to substitute this equation in the above equation, this term integral minus infinity plus infinity g of t multiplied with x of t dt. So that means there is no square over here. So if I try to, this can be written as, this is actually equals to Eg multiplied with Ex, energy of the signal G of t, energy of the signal Ex. So I can able to write like this. So if I try to put this 2, that means the power 2, if I try to take it to the right side, then you will be having this integration will be less than or equals to, this integration will be less than or equals to plus or minus under root Eg and Ex. So those things, if I try to substitute over here, I can able to say that my Cn also will be having the values ranging from +1 and -1. Cn is also having the values between +1 and -1. Okay, so you try to check it for a while. So if I try to consider plus root, if I try to consider plus square root of EG multiplied with EX, if I consider this thing in place of this, if I because this, when I try to consider this, then this is the maximum value that you are going to have. So if I try to substitute it over here, then you will be having a +1 value and minus you will be having over here. So that is the minimum value that you are going to have. Okay, so that is the minimum value that you are going to have. And remember one thing, this equality sign will be valid if and only if your g of t is equals to some k into c of t. That means if you try to write g of t in terms of k into c of t, that's what I was supposed to write earlier, k or lambda, whichever it is. So if g of t is equal to some k into x of t, then you will be having these two are equal. Okay, otherwise you will be having the Cn, the correlation coefficient between two signals. The correlation coefficient between two signals, even for the signals also, it will be in the range of -1 to +1. Okay, so when Cn is equals to 1, that is when Cn is equals to 1, I'll tell you one thing. Yeah. Let me use this thing. So if g of t is equals to k into x of t, if g of t is equals to k into x of t, you will be having Cn value 1. Cn value. If k is negative means here actually this k Cn is equals to 1 if k is positive. If k is negative, then you will be having Cn is equals to -1. And if k is equals to 0, then you will be having Cn is equals to 0. And this is the case where we are going to be having mostly similar. And here mostly dissimilar. I'll give you an example, don't worry. I'll give you an example. Cn is equals to 0, orthogonal. So we are going to compare two signals, right? Actually, what we are going to compare, Cn is equals to 1, Cn is equals to +1 means what actually it says? It says that those two signals are similar to each other. And Cn is equals to -1, it says that it is those two signals are highly dissimilar. Highly dissimilar. Okay, and Cn is equals to 0. So what actually you are going to compare here? Actually, we are going to compare the shapes of the signals. Okay, when you take the example, it will be very good. As I told you, when Cn is equals to 0, you may consider that as the signals or the vectors. Those two will be considered as something as very best friends. Very best friends. Very similar. Very similar means almost you will be having the same features for both the signals. Similar features, highly similar features you'll be having. That's what the best friends means. Whatever they one person thinks the same thing, the other person, they are like-minded people. Actually, they are like-minded people. When I try to consider Cn is equals to -1, they were exactly opposite. That means they were worst enemies. If a person is trying to do something, the enemy will be doing exactly opposite to that of that. So Cn is equals to -1 will be something like that. And Cn is equals to +1 is best friends. Cn is equals to -1 is worst friends. Worst enemies, actually. It's not worst friends, worst enemies. Worst enemies is completely different from worst friends. Okay, and there is a case of Cn is equals to 0. Cn is equals to 0 means you can consider it as completely strangers. One person doesn't have any effect on the other person. I hope you people are following what I am saying. Highly dissimilar is completely different from orthogonal. Highly dissimilar is completely different from orthogonal. Okay, so let's take an example so that we will be getting the similarity between the signals. Okay, before going to that, I'll try to define the correlation coefficient Cn for the complex signals. So correlation coefficient Cn for the complex signals is given by Cn for complex signals is given by Cn is equals to, of course, for complex signals also you can able to define the energy of the signal Eg and Ex, and the only difference that you can able to see is integral minus infinity to infinity. You are supposed to keep g of t multiplied with x star of t dt. This is the way how you are going to define the correlation coefficient, and even here also you will be having uh, the correlation coefficient ranging from +1 and -1. Okay, let's take an example now. So this example will try to clarify all your queries. Let me take a special color here. So let me take this example. So I'll be giving you a set of signals and we'll try to calculate the correlation coefficient between these two signals. Okay, so the very first signal what I'm going to define is x of t. So let me define x of t as something like this. So let me consider this is 0 and this is 5, and let me consider this is t. 0, 5, and this is 1. Let me assume this is x of t. Now you are asked to calculate Cn. Calculate Cn. Calculate Cn between for x of t and gi of t. Actually, what is gi of t? I'm going to define over here. Let me start with g1 of t. G1 of t, I would like to give the same 0, 5, this is t, and this is 1. So this, you people, you may try if you want. Okay, so likewise G2 of t, I'll be giving a similar waveform, but I'll reduce the amplitude to 0.5 now. 0, 5, and here the point is 0.5. What is our aim over here? We would like to calculate the similarity between two signals. Okay, that is our aim. Okay, let me go down. I'll try to define the third one. The third one will be something like this, or else let me take a razor. Okay, so let me consider this thing. This is t, and I'll be having something like this. Of course, this is 5, but this is -1. So let this be g3 of t. Yeah, I even want to have g4 of t. We'll try to see the similarity, how the signal x of t is similar to these three. So g4 of t, I am going to have something like this. So this is 0 again, and this is 5, and it is going to start from 1. This is 1, and the expression is given by e to the power of minus t by 5. This is g4 of t. G5 of t will be having something like this. Okay, of course this is 1 and this is 0. Somewhere here you will be having 5, and the expression is given as e to the power of minus t. And the last one, this is g5 of t, and the last one, let me take it as g6 of t. I'll be considering a simple sinusoidal signal. So this is 5. Of course, amplitude goes to +1, and this is -1, and you can able to have this is 5, and the expression is given as psi 2 pi t. Okay, now let us try to see how these things happens. Okay, Okay, let me start with the g1 of t and x of t. So we have the expression. We have the expression for the correlation coefficient. Cn is equals to 1 upon root ex eg integral minus infinity plus infinity x of t g of t dt. This is the expression for C, the correlation coefficient C of t. So let us calculate ex energy of the signal. Ex is equals to integral minus infinity to infinity x of t, x square of t is x square of t. Actually I can replace this as a 0 to 5. I can replace this as 0 to 5 1 dt. So you'll be getting ex as 5. Ex is equals to 5. Likewise, let us calculate the energy for all the signals. So for this, Ex is equals to, of course, because it's the same signal, I'll be having 5. And here you can be having Ex is equals to, so you'll be having 0 to 5, integral 0 to 5. So 0.5 whole square, because this is x square of t dt. So 0.5 whole square is 0.25. So 0.25 dt. So you'll be having 0.25 multiplied with the 5. That means 1.25 will be having. So likewise, if you try to calculate the energy of this signal will be minus 1 whole square, it will be 5 you'll be having. Okay, let me consider this as EG1, EG2, EG3, and even EG4 and EG5. If you try to calculate, I can write it over here because I already calculated it. I'll write it over here. So EG4 will be 2. EG4 will be 2.1617. You people can try it. And even EG5 will be 0.5. And this one will be EG6 will be 1. So you'll be having integral 0 to 5, integral 0 to 5 sine square 2 pi by 2 pi t dt. You people can calculate this thing. You people can calculate this thing. Okay. Now if you come over here, the next thing what we are supposed to have is okay. We would like to calculate this thing. Okay. So if I try to calculate integral minus okay, for this particular case, integral 0 to 5 1 dt, right? So this will be equals to 5, and hence you can able to write Cn is equals to 1. I hope you people are following what I'm saying. So this will be x of t multiplied with g of t. X of t and g of t both are same. Here x of t and g of t both are same, and hence you will be having x of t and g of t both are same, g1 of t for that matter. So between the limits 0 to 5, so 1 into 1 dt, so you'll be getting 5. Now if I try to consider the second one, integral 0 to 5, x of t is 1 and g of t is 0.5. So 1 multiplied with 0.5, 1 multiplied with 0.5, and remember one thing, 1 multiplied with 0.5 dt we are going to have, right? So it will be something like 0.5 multiplied with 5, that is equals to 1.25. So that means this term is 1.25 here, and the denominator you will be having under root x so your Cn is
2.5, sir.
Yeah, which one?
2.5, sir, there.
Yeah, this is 2.5. 5 as 25. So 2.5 divided by under root ex and eg. Ex is equals to 5. 5 multiplied with 1.25. 5 multiplied with 1.25, how much you'll be getting?
6.25.
How much?
6.25, sir.
6.25. So under root 6.25 means you'll be getting 2.5. So this will be equals to 1. I hope you people are following what I'm saying. So one important point what I would like to say is the correlation coefficient Cn is equals to 1 for these two, because of course this is same as this one. So you may expect that Cn is equals to 1, but this is this same as this one? If you try to see it, the amplitude is little different. When you try to define the correlation coefficient, one important point we define for the vectors. What is the point? What is that point is? It should be independent of the magnitude. So the concept, if I try to apply for the signals, it should be independent to the amplitude of the signal, because amplitude is directly related to the energy. So that means it is actually comparing the shape of the signals. That is one of the important things that you should know. That is important thing that you should know. That means the shape of x of t and g2 of t both are same, except for the amplitude. Yeah, amplitude. See, I can able to calculate the similarity between g bar and x bar. Okay, if these two are in the same direction, that means if theta is equals to 0, then I can able to say that these two are similar. Then if I try to multiply g bar with some 10 into g bar and x bar, so then also those two are similar because the angle is 0. And the correlation coefficient does not have the contribution of its magnitude. It should be independent of the magnitude. And that is the equation of what we have derived. Our correlation coefficient is independent of the magnitude, is independent of the amplitude. Amplitude in the sense, it is independent of the energy of the signal. If you try to increase the energy, it doesn't mean that you'll be having more similarity. It's not something like that. It is actually comparing the shape of the signal. Now, if I try to go to the G3 of t, I want you people to try it. Okay, let me do it. Let me do that thing, because I have done this thing also. So now this thing I would like to calculate. The numerator part, integral 0 to 5. So what will be x of t multiplied with g of t? X of t is 1 and g of t is -1. You'll be having -1 into dt. So you'll be having -5. So the numerator is -5 and denominator ex is equals to 5 and eg is equals to 5. So under root you'll be having 5. So that means you'll be having Cn is equals to -1. Cn is equals to -1. So Cn is equals to -1 means these are exactly opposite. Don't get confused. It is also again amplitude. So magnitude of the amplitude you are saying no. So it's not something about the amplitude actually. Here it is exactly up. The amplitude is exactly reverse. The shape is exactly reverse as that of the one which we are seeing it x of t. So theta is equals to 0, theta is equals to 180 degrees, or theta is equals to 180 degrees. Yeah, they were exactly opposite to each other. So there we are going to have the similarity. And we call that as dissimilar, highly dissimilar. So in that context, I can able to say that the signal x of t and g3 of t are highly dissimilar. Highly dissimilar. Okay. Now, if I try to calculate the correlation coefficient for this g4 of t, correlation coefficient of g4 of t, I have did it, and it was found to be as correlation coefficient for g4 of t Cn is equals to, yeah, can anyone say, okay, fine, let me make a small logical question here. Let me show the signals and then I'll ask the questions. Okay, fine. Okay, fine. So I just want you people to make a comment on the correlation coefficients of the signals for g4 of t, g5 of t. At least let us stick on to these two. So, and my original signal is this g1 of t itself, because g1 of t and x of t both are same. Now, if you are asked to calculate the correlation coefficient for g4 of t and g5 of t, because which one will be having more value? Whether it is the correlation coefficient for g5 of t is more or correlation coefficient for g4 of t is more? Rough guess before calculation. So calculation anyway we will do it. I'll give you the numbers. So without doing the calculation, if you are asked to find out the correlation coefficient between that G1 of t and G4 of t, G1 of t and G5 of t, so with the G1 of t, whether G4 of t is more correlated or G5 of t is more correlated?
G4 of t, sir.
G4 of t is correlated because if you try to observe the shape of the signals, G4 of t is slowly decreasing, whereas G5 of t, the decrement rate is very high. So if you try to compare the shape of the signals, then G1 of t and G4 of t will be having more similarity index as compared with the similarity index of G1 of t and G5 of t. Mathematically also, if you try to calculate, I will be giving you the values, the correlation coefficient for G4 of t. G4 of t and the original signal x of t is found to be as 2 point. No, it's not 2 point. Actually, it is yeah, it should not be 2 point. Yeah, for this G5 of t, this is something like 0.5. So can someone please calculate it? Yeah, let us try to do that thing. Anyway, let us do it. So you'll be getting I wonder how actually what I have written over here is the correlation coefficient for this will be 2.16 divided by yeah, let me do it anyway. So the numerator, if I try to calculate integral 0 to 5 e power minus t by 5. This is g of t and that is 1 dt, right? This is what we will be having, and 1 by root, that is 5 multiplied with the energy of this is 2.1617. 2.1617. Yeah, this I already calculated. I'm sorry. G4 of t, I'll be getting Cn is equals to, oh yeah, anyway, if you people calculate this integration, you'll be getting Cn is equals to, I'm sorry, I have noted down here, 0.961, whereas for this, it will be 0.628. 0.628 between this one and this one. Okay. So if you try to see, if you try to compare whatever the argument that we have done, because G5 of t is going to have less similarity index as compared with that of the G4 of t with respect to the signal x of t. So this is what the correlation coefficients what we are going to have. Cn is equals to 0.6 and here it is. That means more or less this is very close to the signal, original signal x of t. This is very close to the original signal. This is less similar as compared with that of the G4 of t. Okay. Now the most important thing is this last one. So if I try to calculate the correlation coefficient for this, so integral 0 to 5 sine Cn I'm calculating. Actually, the numerator integration I'm trying to calculate now. Sine 5 into 5 will be there. 5 I am keeping it outside. Sine 2 pi t dt. So sine 2 pi t dt between 0 to 5, if I try to do it. So sine 2 pi means minus cos 2 pi, right? So minus cos 2 pi means cos 2 pi t will be getting. Cos 2 pi means 5 to 10. Cos 10 pi. Cos 10 pi is 1. Cos 10 pi is 1 minus cos 0. Cos 0 is 1. So this will goes to 0. I hope you people are getting how I am doing this integration. So ultimately what I would like to say is Cn is equal to 0. What I mean to say is the signal G6 of t is orthogonal to the original signal. The signal G6 of t is orthogonal to the original signal, means that is x of t. So G6 of t is very orthogonal to this x of t. That means these two are completely strangers. These two are completely strangers. So that is the only thing what I can able to say at this particular point. So Cn is to measure the similarity of the wave shapes. So now I'll give you a logical thinking question to you. could you please let me know where we will be assessing the shapes of the signals? The students who are attending this lecture, I am asking you the question. So can you come across a place, or can you come across an application where we are supposed to calculate the similarity between two signals? Is there any need of calculating the similarity similarity between two signals? Can anyone come up?
Convolution.
Yeah, as such, the term convolution, it's not actually calculating the similarity between two signals. I don't know whether you are from second year, third year, or final year, but convolution operation will be helpful to find out the response of a system. So if you would like to calculate the response of a system, that means because our participant has said that it is convolution, I'll just give you where the convolution will be. So if I have a system with impulse response, what is this impulse response? Might be the secondary students might don't know, but anyway, x of t is the input of the system and h of t is the impulse response. And if you are supposed to calculate y of t, then you will be performing the convolution between x of t and h of t. Here we were not bothered about the shape of the signals, but what I want, my question is something like this. I just want you to be able to tell me an application where you can able to assess, or the need of comparing two signals will arise.
In communication, sir, at the transmitting end and receiving end.
Could you be please clear about that? I just want you to give a little bit more explanation on that.
Sir, we want to get the actual signal so that we can get exact information. So,
Okay. Okay, fine. Because a friend has told that it is communication, I'll just give you some details about this communication now. Yes, communication is one example. So how this signal comparison is going to be used in communications? The thing is, we will be having the transmitter and we'll be having the receiver over here. And in between, channel will be there. Whether it is a wired channel or a wireless channel, we were not that much bothered as of now. Channel, I am just writing it as channel, whether it is wired or wireless channel. So in binary communication, in a digital communication, let me be more specific, we will be sending bits 1 0 1 0 1 1. These are the bit streams that we are going to send in a digital communication. The digital communication means we will be dealing with only with the bits, right? So we will be sending the digits. So actually, for second years, we don't actually send 1. Instead, in place of 1, we will be sending signal 1. S1 signal I will be transmitting. In place of 0, I will be sending the signal S0. So you can take any signal that you would like to have. You can take any signal so I will be sending some signal S1, I will be sending some signal S0. These two I'll try to consider. And whenever the bit 1 comes, I'll push signal S1. Whenever the bit 0 comes, I'll push signal S0. Now at the receiver end, I should sit over here and I should identify whether the receiver signal is either S1 or S0. So what I'll try to do to the receiver, I'll be giving the information. I send two signals, signal S0 and signal S1 I am sending. So signal S0 will be representing the bit 0 and signal S1 will be representing the bit 1. Signal S1 is representing the bit 1. So if that is the case, if this information is already given to this particular receiver, what this receiver will do is, okay, fine, let the first bit is 1, so S1 will be transmitted over here. Okay, S1 is transmitted, S1 is received over here. Bus. So and the receiver doesn't know whether the received signal is S1 or S0. So now what I'll try to do, he will be calculating the correlation between the received signal and the available two signals. So between S1 and S0, I'll try to calculate the correlation. I'll calculate the correlation coefficient. So between S1 and S1, so because the signal S1 and this S1, these two are highly similar, you will be getting high correlation coefficient if I try to do the correlation between these two. And if we try to calculate the correlation between these two, you will be having the correlation coefficient minimum. Okay. So based on that, okay, because I got the correlation, high correlation coefficient between these two signals, I can able to take the decision that the received bit is 1. I'll take the decision. And the most important thing that you should be able to do is you should select these two signals in such a way that these two are highly dissimilar. That is one of the important points that you are supposed to have. Highly dissimilar. What do you mean by this highly dissimilar? Highly dissimilar means we need to have Cn is equals to -1. Cn between S1 of t and S0 of t. We should have the similarity index Cn is equals to -1. Yes, secondary people, they might be knowing this antipodal scheme. Or secondary, even finalists also they don't know. Antipodal means I'll be using S1 as a sine or cos. A cos omega t I'll be using. Whereas S0 of t, I'll be using minus a cos omega t. Minus cos omega t. And if you try to calculate the correlation between these two, you might be wondering, again I'm saying, this is actually what? This is equals to a cos pi plus omega t. The phase angle is actually 90 degrees, 180 degrees. Cos pi plus theta means it will be coming into the third quadrant. All silver teacups. Third quadrant cos is negative. That's the reason why you will be writing it as minus a cos omega t. The contribution of minus is because of the having 180 degrees phase shift. And this we will call it as antipodal scheme. You people might be knowing this quadrature phase shift modulation, QPSK. See, usually in place of this antipodal, you may go with orthogonal signals also. Orthogonal signals means I can use S1 is equals to a cos omega t, S0 is equals to a sin omega t. The reason sin omega t means that the 90 sin cos 90 minus theta you can keep. So that means 90 degrees phase shift you can able to have. That also can be possible. So orthogonal signals you can use. There are specific advantages if you try to use orthogonal signals in communication. There are specific examples, specific advantages that we will be having if we try to use orthogonal signals in communication. Okay. So this is the place where we will be calculating the similarity between two signals. Okay. Now, that means in digital communication, to be more specific, we will be calculating the correlation between or similarity between two signals. There, this correlation coefficient might be useful. This is one conclusion that we can able to draw as of now, and we already judged or we already decided that the correlation coefficient should be between -1 to +1 only. And it should be independent of the amplitude. It should be independent of the magnitude of the vector if it is in the vector's case. Okay. So this is one application where we will be calculating the similarity between two signals. Is there any other application where you can able to, where the need of calculating the similarity between two signals will be there? Participants, please. Anyone, please answer. Total 13 people were there, if I'm not wrong. I just checked it. So among those 13, I can remove those two also. So only 11 people were there. Yeah, 11 people. Can I get the answer for this? I just want to know the application where we will be calculating the similarity between two signals. Anyone? If you give small clue, that itself is sufficient. I can able to make a nice explanation of that. Okay. I thought some message. No message here, right? So yeah. Yeah, one good application of calculating the similarity between two signals is radar. Radar. So I'll be giving you a brief explanation of why the need will arises. Okay. So in radars also, the second example application is application 2. Application 2. In radars, we'll be calculating the similarity between the need of calculating the similarity between two signals. So what we'll try to do is there will be an antenna. It will be radiating some signal. For the timing, let me assume some sinusoidal, and there will be some target over here. Some target is there. Aircraft. So radar means the radar. Radar means radio detection and ranging. A means end actually. Let me write end also. Actually, R A D A R. That is the reason why we will be calling it as radar. So what is this radio means? We'll be dealing with the radio signals. Radio signals means electromagnetic signals. So all electromagnetic signals ranging from some few kilohertz to some gigahertz. You'll be considering as radio RF frequency, radio frequency. Radio means all electromagnetic signals will be considering as radio signals. So we'll be considering the electromagnetic signals, or we'll be utilizing electromagnetic signals for detection. For detection and ranging. Ranging means to find out the range of the target. For detecting the target, for finding out or calculating the range of the target, we will be using this radio signals or radio frequency signals. So that is the reason why we call it as a radar. But nowadays, instead of calculating the range, that means in addition to calculating the range of the target, there are many applications of these radars. So nowadays, radars can give you the images also. Radars can give you the velocity also, because particularly the traffic police will be having a type of radar which will be identifying the velocity of the moving vehicles. If you would like to find out the velocity of the moving vehicles, actually the principle that was being used over there is the Doppler frequency shift. Okay, so radars has many applications nowadays. Many applications. Okay, so the name radar actually at the time was given just for detecting the target, whether the enemy target is there, enemy or for that matter any target is there or not, and if at all target is there, at what range it is there. So to identify that, people use radars. So what happens is there will be a antenna that will be transmitting the signal. Some signal S of t will be transmitted. So, and if there is any target available, what happens is the signal will go and hit the target, and the portion of the signal will be reflected back. Portion of the signal will be reflected back, and at the receiver end we will be calculating the correlation between or we will calculate the similarity between the transmitted waveform and the received waveform. If there is no target, then you don't find any received signal, or the received signal will be only noise. And if you try to calculate the similarity between the transmitted signal and the noise, obviously you will be getting a very low value of the correlation coefficient. It might be somewhere negative also. I believe you people are understanding what I'm saying. So what actually we will try to do is, We will send a signal, no signal, similar to that of the digital communication. Digital communication, we are sending two signals, S1 of t and S0 of t. So at the receiver end, what we will try to do, the received signal, we will try to calculate the similarity index. That means the correlation coefficient between the received signal and the signal that we are transmitting. Between these two, we will try to calculate the similarity index. And if it is only noise, if there is no target, then the similarity index between the similarity index between the received signal, received noise and the transmitted signal will be very small value you will be getting. Very small value you will be getting. Okay, so this is another application where we are going to use this correlation concept. Correlation means the similarity between two waveforms. Similarity between two signals will be using even in the radars also. A similar application you will be having even for the sonar. Sonar means the sound signals there we will use, and we will transmit the sound signals. That means the known signal will transmit, and we will try to receive the signal, and we will calculate the similarity between the transmitted signal and the received signal. If there is any similarity between these two, then you may say that there is some target. Otherwise, you can able to say that there is no target. So there are many applications where even in electronic warfare applications also will be using this similarity between two waveforms. So the thing what we have derived now, that means the correlation coefficient will be utilized in many applications. So this is what I would like to conclude as of now. Now let's go ahead with this. So does the correlation coefficient itself is sufficient? Will it solve our problem to find out the similarity between two signals? So to answer that question, you have to consider a special case that will be happening in the radars. So what is that special case? I'll be giving you an example. So I have a signal x of t. Let me assume that this is the signal x of t. Usually this signal will not be like this. What I mean to say is the signal x of t is being radiated towards the target to identify in a particular radar application. Radar application, as I told you, we will be transmitting some signal, right? So let us assume that x of t is the signal that is being radiated. Okay. So now what happens? The signal will go and hit the target, and it will come back, right? So this is some t and this is 0. Let me show capital T. So it will come back, and the received signal will be something like this. The received signal, let us assume that there is no noise is added. Let us assume that there is no distortion. Let us assume that any type of disturbances that do exist in between in the wireless medium, wireless channel, let us assume all those things were not there, and assuming that the received signal will be something like this. So it will be getting complex. And let us assume that this is the delay that we are going to have for the signal to travel from the transmitting antenna to the target, and again back to the receiving antenna. So actually radars, there are two types of radars, bistatic radar and monostatic radar. Bistatic radar means it will be using two antennas, one for transmitter and one for receiver, whereas the monostatic radars will be having only single antenna, and single antenna will be used for both transmitting and receiving. Okay, let us assume that this is the delay that is going to happen. Delay, and I'll be representing it with tau. I'll be representing it with tau. Okay, now this is the case what we are going to have. Let me assume this is some g of t, and I ask you to calculate Cn. Of course, the energy of x of t, energy of g of t you will be calculating, and I will be concentrating mostly on the numerator integration, that is integral x of t and g of t, and I'll be putting minus infinity plus infinity. So students, can you give me the answer for this question? Integral minus infinity plus infinity x of t g of t, for x of t this one and g of t this one, what is the value? At least one person.
0.
0. That's right. Thank you. 0. Fine. What this mean? Even though the two signals are same, because they were departed, or they have the delay of tau units, it is saying that there is no correlation between the signal x of t and g of t, but actually there is a correlation. So because of this reason, instead of defining the correlation coefficient, we will be calculating the correlation, which is a function of time. To be more specific, it is a function of delay, and we represent that as psi. Let me consider xg of tau, and the equation is given as integral minus infinity to plus infinity x of t g of t plus tau d t plus tau dt. Don't be confused about this thing. This equation says that, okay, fine. Actually, what we are going to do, we are going to multiply the signal x of t and g of t, and then we calculate the integration. So here, why it has been 0 means, if I try to multiply x of t and g of t, if I try to get the product x of t multiplied with the g of t, I'll try to use different colors over here. Let me use red color to define this thing. So this is what the transmitted signal is. This is what the transmitted signal is. And let me use blue color. And the received signal is, let me assume that it is somewhere over here. So let me assume that this is my received signal. More or less the same shape I am using. Yeah, the transmitted signal will be 0 from here onwards. And even the received signal will be 0 if I try to do it from here onwards. Okay. Now, if I try to multiply this red curve with this blue curve is 0. This is 0. And the red curve is some value. So blue curve multiplied with red curve means you will be getting 0, right? So that is the reason why you will be having 0 here up to this particular point, because here this is it is showing some value over here, but here it is 0. So if I try to multiply these things, we will be getting 0. So likewise here both are zeros, no issue. Now if I try to move over here, the blue color is going to have some value, but red color is going to have 0, and that is the reason why you are going to have 0. That means the product x of t and g of t is going to have 0 over here. Now, after calculating the product, you are supposed to calculate the area under the curve. So because this is very flat, green curve is very flat, so integral minus infinity to plus infinity, it will be 0 only. So that is the reason why you are going to have the correlation coefficient Cn is equals to 0. Now, what this equation says is fine. Now also you do the same thing. X of t is this red line, red curve. G of t plus tau. Now it will be a function of tau. It will be a function of tau means, instead of defining the Cn value, the constant, you are going to get a function of tau. Function of tau means I will be having tau here. And this is psi x g of tau. Okay, when tau is equal to 0, when there is no delay, so this is the case what we are going to have. When there is no delay, then x of t multiplied with g of t, that means tau is equal to 0, I'll be having the amplitude value 0. And if I try to consider tau is equal to some plus 1, tau is equal to plus 1 means, whether it is right shift or left shift. So tau is equal to plus 1 means right shift or left shift?
Left.
So left shift means you are going to move this curve, the blue curve, little bit left.
Shift.
Okay, so that means as we try to increase the value of tau, you will be having 0 only. The moment when this curve touches this one, that means when both are non-zeros, you will be having a value and that will be going to maximum, and then it will be going to minimum, and then it will be something. And you can have the tau value negative also. Right shift also you can have. If you go to the right shift, then you will be having all zeros here. So that means the moment when this curve matches to the transmitted signal exactly, there you will be having the maximum value. So that means the moment when you try to define this correlation, which is a function of the time delay tau, you will be finding the similarity index, no doubt in that. And in addition to that, you can able to find out at what time the signal is being received, which is very, very important in the case of radars. Why? Because the time delay will help us to find out the range of the target. So we all know that velocity is equal to distance traveled by time. velocity is equals to distance traveled by time. So for electromagnetic signals, this velocity is c. This implies c is equals to distance traveled. Actually, if I try to consider from the antenna to the target tx, if I try to consider the distance as r is the range. So this waveform is traveling this time one time, and the other, that means to and fro. You'll be having the total distance that is covered is 2r divided by the time. So c, we all know c is equals to 3 into 10 to the power of 8 meters per second for electromagnetic signals. 2r, actually we would like to find out the range of the target, and if someone provides me the time value, then I can able to calculate the range value. This time means actually this will help us to identify the delay. So from this correlation function, which is a function of tau, time delay, you can able to specify the time delay at which you are going to have the peak. So once you get the time delay and substitute over here, then you will be having the range equation r is equals to c into tau divided by 2. Tau is the delay that is going to happen for the signal to reach the ground station from the time when it is being transmitted. So from the time when it is being transmitted, I'll try to make a note of it, and then I'll wait till the received signal. That means I'll wait when the peak is going to occur. So from this 0th location to the place where the peak is occurring, you can able to define the time delay, and c into tau divided by 2, you'll be getting the range of the target. So correlation coefficient doesn't solve our problem. We have to rely upon the correlation function. Correlation function is a function of tau. Tau is a time delay. And the most important thing is here you can able to keep plus or minus. It doesn't have any problem. It doesn't have any problem. And for that matter, if you would like to shift this or this, that also it won't create any problem. You can even shift this also in place of this. So finally, what I would like to say is this correlation coefficient psi x g of tau, you can also write it as integral minus infinity to infinity x of t plus or minus tau into g of t dt. And most important thing, you are going to perform the differentiation or integration with respect to t, because this is the time axis. I should show over here. So you are supposed to calculate the integration over here. You are supposed to show the integration over here. This is the time axis. So you should perform the integration with respect to t. Those people who also know the convolution, remember there you are going to calculate the convolution with respect to tau. And if you want me to write that equation, this is tau and this is tau minus t you will be having. Okay, when we try to come up with the convolution, I will be letting you know. See, correlation is very simple to remember. Okay, it's just integrating with respect to t. So x of t, gt, dt we are going to have. Okay, so this is what I can able to say as of now. Okay, now, so I'll stop over here. The correlation concept, I'll stop over here. This correlation will help us to identify the similarity. There is a self-correlation. Self-correlation means we'll call it as autocorrelation. Autocorrelation. That means you'll be calculating the correlation between two signals, two same signals. So that you will be representing it as psi x of tau and is equals to integral minus infinity to plus infinity x of t multiplied with x of t plus or minus tau dt. Does this have any physical significance? Yes, it is having some physical significance. Might be people who don't know about the Fourier transform. Even if you know about the Fourier transform, if you try to calculate this Fourier transform of this autocorrelation function, you will be getting power spectral density. Fourier transform, this is called autocorrelation function. This is called autocorrelation function, and the Fourier transform of autocorrelation function is Fourier transform of autocorrelation function. You'll be getting the power spectral density. Gives you the power spectral density. Feeling bored? Fine. I'll be giving you some nice examples, nice Matlab demonstration in the next 20 minutes. And before that, I just want to give some introduction about the image processing. So whatever the equation that we had now, that means correlation, do also applicable correlation for two-dimensional signals is also applicable for 2D signals. What is that mathematical equation and what is the purpose of? First of all, what is this two-dimensional equation? Let us try to see. So we, as of now, we have seen three types of signals. The first signal is energy and power signals. Energy and power. Next one is real and complex signals. Real and complex. And the third one is now what we are going to see. One-dimensional and 2D signals. So I'll be talking about this 1D and 2D signals for a while now, and then I'll be moving on to Matlab demonstrations. Okay. Okay. What is 1D signal? X of t. It is a one-dimensional signal. Okay. F of t is a one-dimensional signal. F of x is a one-dimensional signal. Why? Because it is depending upon one independent variable. Whether it is x or t, doesn't matter. It will be depending upon one independent variable. One independent, actually, it is not dependent. One independent variable. And if you have a signal or function which is depending upon two variables, like f of x comma y. So here x is one independent variable, y is one independent variable, and the function what you are going to have, this is called 2D signals. I'll give you an example. X of t is equals to sine omega t. So if you try to plot the signal, so this is time axis, this is x of t. The signal or the function is going to vary with respect to the time t. I can able to write this as, that means with respect to time, this x-axis is a time axis. So if time increases, the function also gets affected. I can able to write f of x is equals to sine omega x. There is no much difference between these two. For here also I will be drawing the same sinusoidal signal. And here I will be considering this as x. And now I can able to say that this x is a spatial. That means with reference to space. So if this is x-axis and this is y-axis, so as the x-coordinate value increases, your function is being spatial coordinate. As x value increases, your function f of x value also goes on increases. Okay. Now, f of x comma y. So let us assume that so at some x value and at some y value, if I try to give the x coordinate and y coordinate, it is giving you the value that is the amplitude. That means at this particular location, let us assume that the amplitude is some 10 at this coordinate and this coordinate. Now, if I try to vary the x coordinate, usually we will be considering this as x coordinate and this is considered as y coordinate. So if I try to consider this, let me assume this is a 2, 2. In place of 2, if I try to go down, in place of x is equals to, I will be making x is equals to 4 and y is equals to, let me assume 2 only. Then I may have here another value 50. So that means here the function f of x comma y is depending upon two independent variables. The x and y are independent variables, and hence we are calling it as two-dimensional signal. And the most important thing is how to represent this two-dimensional signal. You can do this in two ways. By using the 3D graph. So at this particular x value, at this particular y value, I'm going to have, let me assume this much. Let me draw this. So at this particular location, let me assume this is the amplitude what I'm going to have. This is 3D graph. So two independent variables. Here this is x is one independent variable, y is another independent variable, and at these two independent variables, I'm going to have some function value f of x comma y. So in Matlab, usually we can have different ways of representing these two-dimensional signals. The one way is to have this 3D plot. Yeah, we can able to have this 3D plot in Matlab. The second is by making use of the color. What does it mean? What does it mean means I'll be having a 2D image like structure. 2D image like structure. So this is x coordinate and this is y coordinate. There's no doubt in that. X coordinate and y coordinate. And let me assume that this is the one matrix. Let us assume that this is the matrix. And this matrix, let us assume that it is going to take the values from 0 to 255. 0 to 255. So I'll be assigning the colors here. Color band I'll take 0 to 255. So what I'll try to do is 0 means I'll be assuming it has very dark color, and 255 means I'll be assuming it has very bright color. So that means I'll be having very dark color here, and as I move ahead, the darkness goes on, reduces, and when it reaches to this end, that means when it reaches to the value of 255, it will be showing you the very bright white color. That is the pictorial representation of the two-dimensional image. I hope you people are following what I am saying. So two-dimensional signals you can able to represent either in the image format or in the 3D figure. So that's what I would like to show it to you as of now. Okay, let us do the things in Matlab, and let us have a feel on this Matlab demonstration. And most important thing is we do define the correlation function that we have defined for one-dimensional signals for these two-dimensional signals also. That we will try to see it in the next class. Okay, as of now, I just want to demonstrate the representation of the two-dimensional signals. Okay, so people tired? Yeah, 20 people are there. 20 means 20 minus 2, that means 18 people. Yeah, I hope you people are having nice snacks now. Okay, let me go ahead now. So I just want to keep CLC. Yeah, CLC. Oh my god. Okay, fine. Or if you want, I can use this M file also. So yesterday, Roshan has given a nice demonstration. For your clear understanding, I'll be giving a crispy, clear-cut information about this Matlab. Okay, so we are going to have different windows. The very first window, what I would like to say is command window. You can able to run the program even in the command window. Okay, this command window you can able to run the program, or if you want to write a big actually in command window we don't write big programs, we write small.
Matlab presentation is
okay,
sir,
fine.
Matlab presentation
Thank you
is
so
not
much.
visible.
So you're present. Stop presenting. Present now. A window. Matlab. Start. Okay, fine. Now I believe you can able to see my screen. So you can see this editor. Editor name is given over here. So this editor will helps you to write the big programs if at all you would like to write. Otherwise, one-line programs, if you want to do it, you can do it even in the command window also. So for suppose if I want to assign a variable x with value 5, I just wrote it as x is equals to 5. And if you want, I can put semicolon, otherwise you can remove the semicolon also. What's the difference that you are going to have? So if I put the semicolon, the result will not be displayed in the command window. If I remove the semicolon, the result will be displayed in the command window. So the same rule do exist even if you try to run the program, write the program in this editor file called m file. I'll show it to you. And whatever the variables that you are using in your program will be automatically saved in this workspace. Okay, and command history will be storing all the commands that you are being used. So as of now, I just included the semicolon, and then I'm pressing enter. The moment when I press enter, this variable will be enlisted in the workspace. Workspace main role is to enlist all the variables that you are using in your program. It's not only enlisting the variables, it will gives you the type of the variable, the values that was there in the variables, each and every detail related to that variables you will be getting. Okay, because I included semicolon over here, you don't find the result displaying in the command window. Now I'm pressing enter. So you can able to see x is going to have the value 5. If I try to double click over here, x is going to have a value 5, and here it is showing that it is of data type double. It is of data type double. Now if I run the same instruction, I can use the up arrow mark. I don't want to again retype it. I'll just use the up arrow mark. If I use down arrow mark, up arrow marks, I can get the previous instructions that I have executed. So, and now if I try to remove the semicolon, what will happen? I'll try to have the result being displayed in the command window. So instead of using x, let me use y is equals to 5, and now this time I'm not using the semicolon. Now see what's happening. The result y is equals to 5 will be displayed over here, and here x is equals to 5, y is equals to 5, both were enlisted in the workspace. Okay, so to clear the workspace, usually we'll be using the command clear. Clear will clear the workspace, and clc will clear the command window. Now I'm writing the same instructions over here. X is equals to 2, and I kept a semicolon. Y is equals to 3, I kept, and without semicolon. Now if you try to run this, it will ask you to save the program. So it will be giving me the path of saving the program. Even I don't want to save this program. So instead, without saving the program also you can run. So here run section. Run section means you can able to run this. Actually, you can able to write the program in different sections in Matlab. So for the timing, let me run this section so that we will be understanding what is happening over here. X is equals to 2 means the value will not be displayed in the command window. Y is equals to 3 means the value will be displayed in the command window. These two will be enlisted in the workspace. And now I'm running the section. Okay, on the section. So you can able to see y has been displayed in the command window, whereas x is not, and both the variables were displayed over here. Okay, now what I would like to do is I'll try to put 2 percentage symbols, and this is actually section division. Section, let me assume this is 0 2. So now this is section 2. Let me write what you want me to write. Okay, let me define a matrix. So some G is equals to, so 1 space 2 space 3. I just defined a vector, and I kept here at H is equals to, again I'm defining a vector, 5 space 7 space 3, let me assume, and I'm not using the semicolon here. Okay, so even if you keep the initial space or not, it doesn't matter. And remember one thing, here a red line is being observed. You can able to see terminate statement with semicolon to suppress output within a script. That means it is giving us a suggestions. Whenever you find the red line, something like this, if you place the cursor over there, what will happen? It will give some suggestions. This feature is available only in the latest editions of your Matlab. In the old versions, when I did my BTech, MTech, you don't find such prompting statements, such suggestions you don't find. Maybe somewhere 2000, below 2010 versions of Matlab, I think. But maybe beyond that you may able to have these things. Anyway, now I just want to run only section 2. Okay, for your information, I just want to again clear the data and clear the screen also, command window also. Now, if you want me to run the first section, I can run the first section. If you want me to run the second section, I can run the second section. Even if you want to give some other name instead of section 2, you can give your name also. For suppose, let me take the name of one of the participants here, Bhargav Nanda. Okay, let me write Bhargav Nanda. Don't worry. Bhargav, Bhargav, fine. So see, that's a comment. Whenever you write something after percentage symbol, that will be considered as a comment. Okay, unlike C, it won't create any problem of not using the semicolon over here. In C, if you don't use semicolon, the program will not execute. It will give you an error, syntax error. Okay, now I just want to run the second section only. That's the reason why I'm using run section. Even remember one thing, that I haven't saved this file. Okay, I just run the second section. So G is going to be assigned with the values 1, 2, 3. H is also assigned by 5, 7, 3, and the H is being displayed because we don't have the semicolon over here. So now our aim is to represent the two-dimensional, to represent the two-dimensional signal, 2D signal representation, 2D signal. So for that we should define a matrix, right? So let me assume I can use the same variables or I can use different variables as per your wish. So let me use, and this is case sensitive language, as was suggested by Roshan Matthew yesterday. Case sensitive means if there is a difference between small f and capital F. So f is equal, so let me assume, so rand, don't worry about this, what is rand? Rand I, maybe let me consider 20 comma 20. Don't worry about this, what is this rand, but I just want to run this section only. So rand I f1, if you try to see, you are going to have some numbers. 20 by 20 matrix is being generated over here. 20 by 20 matrix is being generated over here. So because I haven't cleared the workspace earlier, it is being showed something like this, and surf surf f1. Let me check it. आपको कुछ दिख रहा है ना? Something is being visible to you, right? I just want to use this. Let me use this. Yeah, this is the 3D curve what I am showing. So at x and y, you are going to have different amplitudes. There are so many commands, surf, mesh, so many were there. If you want, I can straight away show it to you. So I'll just selected the variable f1, and I can go to the apps over here. I should go to the plots over here, and if I try to keep over here, you can see contour, surf, mesh. These three were there, right? And if I go down, the image also you can able to get. Okay, the image representation, if you would like to see, let us try to have a look on this image representation. So now what happens is, at each and every x and y coordinates, you will be having some image, right? So this is what you are going to have. Or I can use even this IM show also. See, IM show, the moment when I try to use it, is giving this one. But I am show images, see. Yeah, these are the values that here. So each and everything is being displayed with a different color based on the value of the amplitude. Okay. In other words, if I try to use contour, yeah, what is this contour? You might be asking the question, right? So I'm just giving you the glimpse of the MATLAB. Okay. So if you carefully observe the shapes, were this is the contour, top view of this image. This is the top view of the image. This will gives you just the contours on it. Contours of. I think I should show the mesh. Mesh. Let me show it. Yeah, this is mesh. Yeah, you may ask me the question every time when I'm plotting the figure. The previous figure I am closing. So without closing also you can able to do it. So for that, what you should do is you should run the command figure. So when I write a figure over here, so it will be opening a new figure window, And after that, this is a new figure 1. This you see the figure 2 name is given here, whereas earlier it is a figure 1. This is by making use of the mesh. Now I just want to compare this with surf. So for that surf, I'm using this figure 2. So now what I'll try to do is I'll just use this F1. I'll go to surf. So now in the figure 2, you have seen the surf. And you can see both are same. What is the difference is you will be having the mesh version. Mesh in the sense yeah, you can see on here both represents the same. So as such, there is no meaning of this, but if you try to read an image, x is equals to IMREAD read. I don't know whether this will execute or not. LE and Lena dot JPG. Let me check it. It is not there. Lena dot JPG doesn't exist. That's what it is showing. Lena dot TIF. Lena dot P. Okay. Anyway, if you want that, I'll get it done. Okay. Anyway. Bin examples. Yeah. See what it is saying is that image is not there. That's what it is saying. So if you want me to go ahead, let me use this DIP 2018. Oh, it is not there. It is showing. Fine. Let me go with pictures. Not even single picture is available over here. Okay, fine. Lena picture. Let me download it for you and then get it displayed. Okay. Don't worry, you have very much patience. Lena.jpg. So she is the girl of Lena. So I'm just, this is one of the important image that we will be having. Okay, let me copy this image and let me paste it over here. Okay, fine. If it doesn't, let me, okay, it is not pasting also. Fine, let me save this then. Save image as desktop. PNG image actually this is. Okay. So now what I'll try to do is I'll just read, because this is a two-dimensional signal. Image is a two-dimensional signal. Okay. So now I should change the folder to the desktop. So you can see so many files were there in the desktop, and this is the image. So I just want to rename it. I'll copy it, escape. Now what I'll try to do, I'll run the save command. Instead of this, I'll write the name as .png because it's a PNG image. I'll put semicolon and then see. So you can see over here 512 by 512 matrix by 3 is also there. What is that 3? We'll try to see a little later. And that means this is 3-dimensional matrix, not even the 2-dimensional image. This is a 3-dimensional matrix. And you can go with IM show, and this is the image that is being displayed. And you cannot represent this with some surface or mesh because this is a 3-dimensional. Instead, you can able to represent this using surface or mesh, but as you are a surf, I believe this will not work, but let me try. X of colon comma 1. I believe this will not work. Oh yeah, it is working. Yeah. You may ask questions. What is this? Is this the Lena? No, it's not Lena. It is something else. Okay, but this is the nice 3D picture what you can able to have. Anyway, with this, I would like to conclude my today's lecture 2. I'll stop recording now, and we'll have some discussion. Stop recording.